All right, this is Mr. Jern here, and I am here to help you with conservation of momentum related problems. In other words, the idea behind conservation of momentum is that the total momentum of all the objects before is equal to the total momentum of all the objects after. So in this example here, we have what's called a perfectly elastic collision. And what that's going to mean is that you get two objects coming together and they bounce off of each other. All right. So what that means is that the momentum of both objects combined together before they bounce will be equal to the momentum of both objects together after they bounce. So in this example, we have here a 2,000 kilogram car moving at 8 meters per second to the east. It's a 1,000 kilogram car that is at rest. The first car is slowed to 4 meters per second and it bounces off the second car. What is the new velocity of the second car? All right, so like all of our questions, we got to realize that the momentum initial total, the total initial momentum is equal to the final total momentum. All right. And since we've got two cars that bounce off each other, we'll start with the beginning. We've got two cars. So we need the momentum of the first car and the momentum of the second car. All right, so I'm going to call this car, the 2,000 kilogram car, I'm going to call car A. The 1,000 kilogram car, I'm going to call car B. Call them whatever you want. It really doesn't matter, just as long as you keep them separate from each other. All right, so what that means is the initial momentum of car A plus the initial momentum of car B will be equal to, and they bounce off each other. They bounce off each other. So will be equal to the final momentum of car A plus the final momentum of car B. Okay. And I'm re-emphasizing the momentums because now we have to use the equation for momentum. That's just going to be mass times velocity for both, for all of them. All right. If you think of it as almost four separate cars, four separate objects, before and after, initial and final. So the initial momentum of car, what I'm calling car A, is, well, just remember momentum. That's a P. Let's try that again. Momentum is mass times velocity, right? So the mass of car A times its initial velocity, that's the first P there, plus the mass of car B and its initial velocity will be equal to, and again, they bounce off each other, so they don't combine. Their masses don't combine. The mass of car A times car A's final velocity plus the mass of car B times car B's final velocity. All right. See what we're doing here? Now that is essentially the physics of it. We've got it set up. You can now plug in the numbers and be done. But let's plug in the numbers. Let's actually figure everything out here. What I'm going to do here is we want to know the new velocity of the second car, right? So we are going to try to solve for this V, this velocity. And so, as I just kind of said, you can plug in all the other numbers and substitute them and then solve if you want to do it that way. I do suggest and I do prefer, but it's just better habit to rearrange all the letters before you solve. So that's what I'm going to do. Okay, so this velocity is being multiplied by a mass. We can't divide until we take care of, because this whole thing's being added. So what I'm going to do is I'm going to subtract mass A, the mass of A times the final velocity of A from both sides. Okay, so minus mass final velocity. That will cancel it out over here. Okay, so that brings us to Well, we got kind of a lot going on here. Mass A. Okay, and like I said, this is good to do. It seems like a kind of tedious, but it does really help a lot. It's very good practice for rearranging things. And it goes a lot faster when you're not explaining it. So the more you do this, the faster it goes. All right, is equal to mass of B times final velocity of B. Okay, we have quite the equation. We're still trying to solve for this velocity, so I'm going to now divide both sides by mass of B. That's going to be this whole thing divided by the mass of B. Okay, nothing cancels out because we have too much. You could do something here, but I'm not going to worry about that right now. You could take let's not even worry about that. Let's just start plugging in some numbers because we now finally have it set up to solve for what we want. And so I'm going to kind of flip it around over here. So the final velocity of B, I'm moving that to the left-hand side of my equation. And now I'm going to plug in my mass and velocity of A initial. So the mass of A is 2,000 kilograms times its initial velocity. You gotta be careful here, 8 meters per second to the east. Okay, east is a positive number. We'll just keep that in mind. I mean, we don't know. East is positive. And when in doubt, we'll stick with, okay, that's east is positive, right? So we're gonna stick with that. So that's mass and velocity of the first car initial. We're gonna add that to the mass and velocity of the other car initial. So, well, hey, look at this. It is at rest. All right, well, let's do this anyway. It's at rest. It is 1,000 kilograms. It's at rest, so 0 meters per second. It's kind of nice because anything times 0 is 0, so we can just call that 0. Oh, that is not a plus. It has a minus, and I just started naturally writing a plus. Let's subtract our mass and velocity final of A. So A again is 2,000 kilograms times its final velocity. It says it's slowed to 4 meters per second. That implies it's still going to the east. It did not bounce back in the opposite direction. It is still going in the same direction. If it did bounce back in the other direction, you would have to use the negative sign to indicate that it is going in the opposite direction. But it is in the same direction. So I'm going to leave that as a positive 4 meters per second. All right, so I'm going to put positive, positive because they're both heading to the east. All right. And that takes care of that. And I got to divide everything by the mass of car B, which is 1,000 kilograms. All right. Well, now, there is some simplification you could do here. I'm going to do just the straight up, I'm just going to put in the calculator as it shows up here so that we could just kind of see everything. But if you're comfortable with doing the simplification, go nuts and do that. So 2,000 times 8 meters per second minus, I'll put this in parentheses, 2,000 times 4. Okay, so divide that by 1,000. And my answer is going to be, well, according to the calculator, it's 8. What does that mean? All right, so I don't need the calculator anymore. Let's take care of that. Go away, calculator. All right, what are the units here? Kilograms on the bottom. Is that even going to cancel out? Okay, what happens is you get kilogram meters per second minus at the top kilogram meters per second, and then all that divided by kilograms. Kilograms is everywhere, so kilograms cancels out. Nothing leaves, or nothing is going to cancel out. Our meters per second. And so I get 8 meters per second. So the new velocity of the second car is going to be 8 meters per second to the east